So in the last session, if you see, we left our session at the problem which I named as matching problem. Okay. So what was that matching problem? I'll again maybe write it over here so that you can put your brains on work and maybe give me some answers. So the question, the matching game was like this. So there are different versions of the game floating around in books or people who work in probability. So there are different things. So one thing is this gambling game. So what is this gambling game? So in that game, you have some N cards. You have these N cards, and these N cards are shuffled. Okay, and N cards are numbered from 1 to N, 1, 2, 3 till N. You have these cards, N cards, which are quite well shuffled. Question was, you will win the game if at least one card appear at its place. Let's suppose if this one card, this card number 1, is at the first place, or if this card number 2 is at the second place, or if the card number 3 is at the, basically if ith card after shuffling is still at ith place, then we call this game that this is a winning game. You will win. Okay, you will win the game. So this is one version of this gambling game. The other version I said is, so if there are people who came to a party, there are let's say N people who came to the party, and they had all the hats, and they threw the hats in the center of the room. So after that, what happened? They are recollecting their hats. So what is the probability that at least one of them will get their hat back? Okay, they will not misplace their hat, they will not get other person's hat, they'll at least get their hat back. So this was the matching problem. You understood the question? किसको question समझ आया? Any thoughts? Okay, let me do it, and second problem you will do it. So here, let me again introduce this. So what I said is, if you have a problem, the first thing is come up with the thing that you think is favorable. So the favorable event here is, so at least one of the cards should be at its original position. So I denoted that with AI. So AI means ith card is at the ith place. So if I write A1, that means first card is at its first place. Or if I write A2, A2 event means second card is at the second place. And now we have N cards in total. So now in order to tell me that at least one card should be at the at its original place. So what I can do is I can say A1 or A2 or A3, something like this, or till AN, because that's what the meaning of this A1. A1 basically means first card at the first place. A2, second card at the second place. So if I do this, either this should be there, or this, or this, or this. That's what I wrote in here. So I said probability of union of all of these AI events. So I goes from 1 to N. Okay, I hope this clarifies things. So what I'm saying over here is, now this thing says me at least one is true. So that's the meaning of this union. Or basically you are saying either this happens, or this happens, or this happens. So or basically means multiple can also happen. It's not that necessary that only A1 will happen or only A2 will happen. This is not only condition. This is or condition. That means this can happen, or this can happen, or this can happen, or they can happen all together. Okay, that's why I said now you at least have a formulation. You at least have a mathematical notion. I told you have to think mathematically. Once you have the problem, you brought symbols in. Okay, you define something, and you have to convince yourself that I have to compute this basically. Once you convince yourself of this, now I hope that you convince yourself of this is the meaning. You have to see, okay, so are all of these events mutually exclusive? Can I directly add these events? Can I directly add them? So then we can figure out, no, these things are not mutually exclusive. Why? How to convince yourself of that? Why? Let's suppose first card is at first place, and we have third card at let's say we have 4, 3. Now we have first and third cards for exactly at their places which were in the original deck. So that means A1, A3 is not equal to 5. So there is some intersection. And there is not just one intersection. I just showed you one example. There are a lot of intersections. So that means these things are not mutually exclusive. So what we should do is we should use inclusion-exclusion principle. Okay, so I said in such cases, okay, so here in this AI intersection A1 intersection A3 is true here. So both of these events are happening together. So that means we at least got one example. You can get more than one example. So this is now the case that these things are not mutually exclusive. So we'll go to the inclusion exclusion principle. So what is that principle? If it is for two events, if we have A1 union A2, okay, again coming back, so the probability of A1 plus probability of A2 plus probability of A1 intersection A2. Okay, this was just for two events. Then I said this can be generalized also. So if I have probability of union of I goes from 1 to N, let's suppose AI. So how we can write it? So summation of probability of ai's. I is equal to 1 to n. So this is like p1, p2, p3, something like this. This is the first term, and then you have to alternately subtract them. So this is actually subtraction. P1 plus this is subtraction. Okay. And then you have to subtract. Or what do you have to subtract? You have to subtract summations which are of 2. Let's suppose I'll write summation of I less than j pi intersection pj. Okay, and this goes from again 1 to n, 1, 2, 2, 3, 3, 4, something like this. And then you again add it. Now you have to add the third intersection. So pi intersection pj intersection pk, something like 3 intersections now. Okay, and again you will have I less than j less than k, something like this. This is probability of these things. Not just pi, I am saying this should be probability of a I aj. So and in between there is intersection, and probability of I less than j less than k, and this should be probability of a I aj and ak, because there will be multiple of these terms. Okay, you'll have to figure out how many. So you have to summation of all these terms. Okay, then you will keep on doing this. Okay, and at the last you will have this either -1, you have -1 raised to n plus 1. So how many terms do you have? Okay, and then you will have the last intersection, probability of a1 till an. Okay, this is the generalized formula that I think this should be that this rather should have been taken as a homework to prove. They have proved this. Okay, generalized version of this. Not able to. Okay, fair enough. Okay, yes, we have a question. Yes, go ahead. Okay, so this thing was for the 2 events. So if you see, we took it to n events. Okay, so why is this -1 and n plus 1? So it depends how many terms do you have in total. So here we had n terms, and accordingly you will put a negative or positive sign. So basically what you have to do, you initially take probability of 1 term, then minus probability of 2 terms, plus probability of 3 terms, plus minus probability of 4 terms. Keep on going till you land at probability of all the intersections, all the terms together. Okay, and now if you see this, so this problem is quite hard if you don't formalize it. If you don't put these notations, this is very hard. Now I know at least this formula is there, and there is an intersection. So what is probability of ai? So what is the probability that a1, probability of a2, because we have to find this, and then we will find also the intersection part. The probability of ai, if you see, one card, ith card should be at ith place, and other cards I don't care. Okay, howsoever they are, I don't care. That means total ways to have these cards in some permutations and factorial. Okay, so what is the probability that at least a1, ith card, is at its own place? So what I'll do is I'll place ith card at its place, then I am left with n minus 1. I am left with n minus 1. I have to arrange them in any order. So n minus 1 factorial. Okay, we have done this in pretty detail. So how many of you agree with this? That probability of ai, that is probability of ith card being at ith place, is this much. Why? Because n factorial is the total combinations, the total permutations possible for these n card to be arranged, and then you have to place one card at its place. So that means one card is fixed, rest n minus 1. So one card is fixed, the rest n minus 1, you can do anything with that. Okay, you can permute them in any way. So what is the number of permutations? N minus 1. So this is the probability that at least one card, not at least, sorry, the ith card will be at its own position, that's ith position. Okay, how many of you agree on this? So all of you agree on this. So ith card, first card at first place. So this is the probability. Now I had to figure out. I'll tell you this problem has a symmetry. Okay, and mathematics respects symmetry. So what is the symmetry? So if I say a1 intersection a2, what is the probability of this? So again the same thing. So in total I have n factorial ways to arrange the cards. Now I have to fix 2 cards. Fix first and second card, and rest n minus 2, howsoever you want them to be. N minus 2 factorial. Okay, this is for the 2 cards. Again, if I have to, let's suppose, now generalize it for k cards, probability of a1 intersection, let's suppose till ak, any k cards. Now what is this saying basically is, take k cards, fix them in place. Now you are left with n minus k cards, arrange them in any possible way. So the probability of this is n minus k factorial divided by n factorial. Okay, I hope you people also agree on this, because these are the terms that are getting used in formula. The first thing that is getting used is these individual terms. Then we have these intersections. Okay, and we could directly see there is a pattern, direct pattern. Now if I use this formula, if I directly use this, I'll say probability of union of I goes from 1 to n ai. So what is it equal to? First take the summation term, summation of I is equal to 1 to n and the probability of ai's. AI, and then the second minus. Let's suppose I'll say I1 or IJ, I and J. So if this is the term I less than J, the probability of AI, AJ. I'm putting comma over here. So comma basically means if I write them together, that means intersection. Okay, and I'll keep on doing this until the last term. And now you see this. Okay, now we'll have to solve this. Now the first thing, AI, we solved it. So for any of these terms, the probability is n minus 1 factorial divided by n factorial. Okay, so this is the probability, n minus 1 factorial divided by n factorial. And then you will have to see, okay, how many such terms will be there? Now these will be n terms. Okay, so these will be n terms. So such n terms will be there because I am taking from I is equal to 1 to n. So such n terms will be there. And probability of one thing is this much. So this is for the first term. And now for the second term, if you see minus probability of this, again you can see it. This is n minus how much? N minus 2, because you are reducing two terms, n minus 2 factorial divided by n factorial. Okay, now how many such terms are there which have these two things? Now this is n choose 2, because the total terms are n. So this is n choose 2 and n choose 2. So how so what is this equal to? This is equal to n factorial divided by n minus 2 factorial. Okay, so this is n choose 2 is equal to n factorial divided by n minus 2 factorial into 2 factorial. Okay, so that I can put it over here. So I can say how many number of these terms are there? N factorial divided by 2 factorial into n minus 2 factorial. Okay, this is going out the screen. Let me do something so that it remains here. 2 factorial n minus 2 factorial. Now if you see this thing is getting cancelled by this. This thing is getting cancelled by this. Okay, this thing over gets cancelled because n into n minus 1 factorial is. So what you can see is, you will see an expression like this. You will see 1. This equals to 1. For the second term, you will see 1 divided by 2 factorial only, because this is only left. 2 factorial is left. And then in the third thing, you will see 1 by 3 factorial. Okay, plus 1 by 4 factorial, and so on. You will keep on seeing this, and at the end you will see 1 divided by n factorial. Okay, for all these terms. So for all these terms, there is only one term. Okay, so this is n choose n. Okay, so this is what you have to do. You land at this. Okay, and here you can write it 1 divided by 1 factorial. Okay, so if you can see this, so this is the expression that we got. Okay, 1 divided by 1 factorial minus 1 divided by 2 factorial plus. So anything that you see of this sort, so the answer basically lies in Taylor's series. Okay, so we can approximate this thing now. We can approximate this. So usually the question will be that what's the probability that no one gets matched. So if you shuffle these cards, so there is the probability that no card gets at its own place, or nobody gets its own head. So we'll do that by 1 minus all of this. So 1 minus all of this over here. So if you see now this 1 minus 0 factorial, and then we'll say minus 1 minus 1 factorial. So this is equal to e to the power minus x. So this is equal to 1 divided by x. 1 divided by e to the power x. Sorry, 1. This is e to the power minus 1. So this is 1 to the power 1 by e. So this is the answer. So basically, if this 1 minus Taylor series is equal to this is 1 by e. So if you have to see, you can again see. So you can just compute this value also. So now you can see this answer over here. This is equal to, let's say this is equal to e. So if you see this over here, this is the answer. So now you can see how this e came into the picture. Okay, this is a separate discussion. This is a separate discussion. So the problem, let's suppose this number is around 0. Say some 333, something like this, 0. some 3. Okay, so this is the answer. Let me again check it if this is the correct answer. Yes. So this comes out to be this, like e to the power minus 1. So e to the power minus 1 is equal to 0.36, not 0.30, 0.36. Okay, so this is actually e to the power 1. So the answer to this basically was 1 minus e to the power x. So this was 1 minus e to the power x. So if you solve the reverse problem, then it just relies to e to the power minus 1. Okay, so here the answer to this was 1 minus e to the power minus 1. Okay, to this. But I said sometimes it's asked in a reverse way also. What is the probability that no card is at its original place, or nobody gets its own hat? What is the probability? So the probability for that is only e to the power minus 1. E to the power minus 1 is the probability that nobody gets their own hat. For 1 minus e to the power minus 1 is the probability that at least one gets its own hat, because they are complementary. So here if you see, this is 0.36. Okay, so this will be 1 minus 0.36. Okay, you see quite high probability, like in 60s. Okay, maybe 64 or something. So this is 0.64. Now I'll give you a trick. You see, if these are infinite cards. Let's see, these are infinite cards. So now you can be in two ways. You can be either optimistic or a pessimist. You can think, oh, these are infinite cards. Let's say if they're infinite cards, maybe at least one card will be at its own place. Why? Because we are having so many cards. At least one will get. But sometimes you will think, but there are so many cards. How everything will be misplaced. Okay, it depends. Some people can say the probability is 0. Probability of this thing happening is 0 with infinite cards. So some will say probability is 1 because at least one card will find its own place. Okay, some will say no, these many cards are there, so no card will get its own place. Some might say that, oh, with these many cards are there, at least there is a possibility that one. And people usually say there is a 0 or a 1 probability depending on how they look at this problem. But you now saw that there is a concrete answer to this. Okay, so what is the answer? That answer is this: 1 minus 1 divided by E. Okay, this is the answer to this question. And you see how probability can hack you some. Even now we have infinite cards. You see, we have infinite cards. I said n cards. N can be towards infinity. Now you can see that why did I show you this problem? Because the first thing is you saw that inclusion exclusion principle seemed quite easy, but when you have to model the problem, oh, it looks daunting sometimes. Okay, and you have to evaluate these things. And there was the symmetry in this problem. So if you respect symmetry, so you can take a lot of these things out of symmetry. And then you saw that there can be sometimes these answers which we don't even expect. Oh, this will happen even if there are infinite cards. I think we have a question. Yes, question. Okay, now and the question for you people that you have to give answers. Okay, if you later on watch this video, so you can pause and then maybe think also what that. Do not directly jump to the solution part, because I usually pause the recording in between when you think and then solve it myself. So when you are revising it, again pause the video this time when I am putting a cut on this, and then you can solve it on your own. The question goes like this. So what is the probability that we have 10, let's say I'll ask you the question and then at the end I'll say what the probability is. So we have 10 married couples. So we have 10 married couples. And these married couples, they want to sit around a table. So there is a round table. Okay, there is this round table around which they want to sit. 10 married couples want to sit around the round table. So the question is, what is the probability that no wife sits next to the husband? Okay, probability no wife sits next to her husband. Okay, I'll give you some time, maybe 5 minutes.
Okay.
So what I'm saying is, first we'll define something. So we'll say, let's denote AI. AI is ith couple. Ith couple is together. Ith couple is staying together. So they want to sit. So what we are doing is, we want to compute the probability that no wife sits next to her husband. So as Fahad rightly pointed, what he said is, we'll make these couples as separate units. So we'll say we have 10 units of this, 1, 2 till let's suppose 10. So we have now defined an event. We said AI is the ith couple together. Okay. So then what do you have to compute? Tell me. What do you want to compute then? Probability of what? So if we see probability of at least one couple sitting together, so we can say probability of union of AI, I goes from 1 to 10. Okay, but this is probability of at least one sits together. But we have to find probability no sits together. That means complement of this. Okay, 1 minus of this. If I have to find none, that means I have to find at least one complement. Okay, I have to find this. Okay, now let's hold on this. Let's hold on to this. So basically, I'll compute this part. If you see, I'll compute this part. So how to compute this part? Tell me. Probability of I goes from 1 to 10 AI. So how to compute this? By using what principle?
जो हमने पिछले वाले प्रॉब्लम में यूज किया था पहले,
inclusion exclusion. Yes, summation of what? Probability of all of these. So I goes from 1 to 10, and then plus summation of I, let's suppose 1 less than I2, something like this, or J. So this is probability of
minus
A I1, A I2, and keep on going.
AI2.
Okay, now we'll have to see, should we directly use this? So we'll have to find at least for one. Let's say what we'll do is we'll say AI intersection AJ. What's the probability of that? We'll find it separately first. Then we'll have to just plug in and we'll see if there is symmetry. Okay, so if you see something of that sort. So what I can do is, if I have just two things. So in circular combination, if usually you have n factorial permutation possible, if it's a linear permutation. If it is a circular permutation, so one permutation misses out. So in circular you have n minus 1 permutations. If you have n places and you want to permute them circularly, because in circular you don't have the point end and there is no concept of end and start. So in circular you will have n minus 1 permutations. That's what in here, if you have, let's say, 20 people, so in circular permutation the number of permutations is 19 factorial. Okay, and you have to reason it also. Okay, I'm giving you the answer right here. So but once you again go through this lecture, so pause here and think, why should it be n minus 1 factorial? Okay, and I give you the reason. In circle there is no concept of end and the start. Okay, and then you have to think it through and convince yourself. So what I said is the total permutations possible is these many things. So this is the total permutations possible. Okay, now what I'm doing is I am fixing, let's say, a couple. If I say I am fixing, let's suppose, one couple. So what I can do is I am fixing in here. I am saying, okay, this couple is fixed and this couple is fixed. So I am taking two couples out of that. That means I am taking how many couples? So that is, we now have left, the total thing that we have left is, let's say, how many people now. So how many, we are taking 2 out of it. Okay, so let's suppose we take n now. We can handle it n together. Okay, so not just this. So we can say probability of n together. Okay, till n. If we have n of these, okay, we have only 10, we'll generalize the problem and then we'll see. If I'm taking n out of it, that means I'm taking 19 minus n factorial. Okay, these many permutations then, because I'm taking n out of these. Okay, how many are left? 19 minus n. Actually, it was 20 minus n, but in permutation, these many possibilities are there. Okay, everybody with me so far? So I'm saying 19 factorial in total. 19 minus n is, if I'm find the intersection of these people, I'm just subtracting n and saying factorial. But now once I picked them up, so I'll have to also arrange them because I'm picking n of these. Okay, now I have n places to fill. Okay, each place I can put husband, I can put that here, or I can drop them. Okay, I have basically 2 possibilities everywhere. So 2 possibilities here, 2 possibilities, 2 here, 2 here, because I can switch them. Husband, wife like this, or husband, wife. I can put husband, wife, or wife, husband. It's the same. So there are 2 possibilities of putting these. You put husband, wife, or wife, husband. Similarly, husband, wife, or wife, husband, something like this. So that means multiplied by 2 to the power how many n possibilities. Okay, so this is the formulation. 2 to the power n and multiplied by this divided by n. So this is for this. So what is the probability? I will have to find probability of AI also. Okay. Well, what is the singular probability? Again, you can do the same thing. So singular probability 19 factorial. So you are taking just, let's suppose, one of these. So you directly use this formula and then fill these things up. Okay, and till here, from this I'll leave you to the calculations. This is just calculations. And here again I showed you that the problem was even, let's suppose, modified differently, but again the same principle got used. So we just model it mathematically, and second step that we did is we resorted to permutation combination and said, okay, how to use inclusion exclusion principle. That's it. Okay, there was nothing more than this in the problem. Is it all right? Can you do some problems of this sort on your own? Okay, I hope with this I'll close this problem sections of basic probability. I'll consider it done here. So now your job is 2 things. The first thing is go through these lectures again, make your combinations, permutations, and in general combinations very strong. Okay, make your counting very strong, and keep on logically reasoning. So whatever problem you see in the real world, try to see if you can compute it somehow by using probability. And this usually is the frequentist approach. So here probably we'll come back to this again. Maybe some of these parts will be again touched. But here I'll conclude this because we did enough examples. I told you how to model probability problems and then how to think about these things. And we did a couple of problems. So here frequentist approach, we'll close it for now, and maybe sometimes we'll revisit this again if it is needed. So but sometimes what happens there, so you cannot, as I said in the previous classes also, so sometimes it's not possible that you can perform the trials again and again. So there you will not be counting things. So per se, you will not have chance of counting. So for let's suppose, for example, if I say, if I give you a question, so what is the probability that this pen is made by Samsung? What is the probability of this pen being made by Samsung? So if you see, this is somewhat a doubtful question, so I cannot perform these trials again and again. Okay, there is no concept of trial in this. There is no concept of performing an experiment using a frequentist approach. So now you will have to have a belief about this. So you will say, I believe probability that this pen will be made by Samsung is, say, 30%, 40%, something like this. Okay, so such things. So initially what we said in frequentist approach, we see trials. Now we are going into a separate direction, basically measuring the measurement of the belief. So probability is basically a measure of belief. So probability is a measure of belief. So in such of the cases where you cannot perform a trial, where you cannot run a trial or frequent test approach, so you resort to this belief. As I said, let's suppose if I have a piece of code, if I say what is the probability that Mahmoud has written it, so there I don't have the I cannot resort to frequent approach where I can perform trials. So I can have a belief probably. I can say I think this code written by Mahmoud, 90% probability is there. So probability that this code written by Mahmoud is 90%. So all of these things come into the belief. So probability is actually a measure of belief. So this thing over here is called personal view of probability. This is called personal view of probability. Okay. So one thing in frequency approaches, we can perform trials, and second thing is we sometimes have to measure the belief. So with this, we have to shift to the conditional probability. Okay. Now you can shift the gears and you can put the title as conditional probability.